In the last couple of lectures, we had taken a look at PN junction diodes, how they are constructed, how they work, and how they behave in a circuit. Today we are going to take that knowledge forward and discuss some very simple diode circuits. In fact, the circuits we are going to talk about today are all familiar ones to all of you. You have seen them in action in your higher secondary course. However, we will point out some perhaps subtle points about them which you may not have seen earlier. But more importantly, this is to be taken as groundwork for the more complicated circuits that are going to come in the future lectures. So the very first circuit that we are going to talk about is essentially the same one that we talked about in the last lecture. This is using the diode as a rectifier. In particular, the half-wave rectifier. The circuit should be a very familiar one. This was the circuit that we used in our last lecture. It's a sinusoidal voltage source, which could be a sinusoidal, say, function generator, or could be an AC source coupled to the circuit via a transformer. But ultimately, it's a sinusoidal source which is connected in series to a diode and a resistance. And the voltage across the resistance is the output. So this is the basic diode circuit that we had studied, and as I said, this is our rectifier. Well, if you put in an input which is sinusoidal, Vp sin omega t, where Vp is the peak voltage and omega of course is the angular frequency, the output, as we studied in the last class, is given by this purple curve here, and this output is unidirectional. Unlike the input which goes both positive and negative, so changes direction, so it's alternating, the output is not. So in a sense, the output is direct current, is always in one direction. After all, this is exactly what the diode is supposed to do. It allows current to flow only in one direction and not in the other. As a result, the voltage across the resistance, which is of course proportional to this current, is also only in one direction and not in the other. Now, what about the voltage drop across the diode? Well, it's obvious that whatever is not dropped across the resistance has to be dropped across the diode. So if you just plotted the voltage drop across a diode, you will get this green curve. So even in the forward direction, there is a voltage drop across the diode. It's not really zero. It's somewhere close to a peak value of so-called cut-in voltage, V gamma. But this is a more careful analysis, a numerical calculation which gives rise to this variation of the diode voltage even in the forward bias. In this case, of course, we have chosen quite a small value of the input voltage in order to describe the operation of the circuit, a value which is not very large compared to V gamma, which is why the peak value of the output voltage looks substantially smaller than the input voltage peak. If you had used, say, a 20 volt peak, then the cut-in voltage would have been a lot smaller than the peak voltage, and this gap that you can see here between the peak of the input voltage and that of the output voltage would have been almost negligible. But what is actually more interesting is, what is the diode voltage when the input is negative? The diode now is reverse biased. No current flows through the diode, which means there is no voltage drop across the output resistance. Of course, that's why this is flat here. But it also means that all the voltage, the entire input voltage, has to be dropped across the diode. So this also tells you one thing, that what is the maximum in reverse voltage which occurs across the diode? That's exactly equal to the peak value of the input voltage. So the peak inverse voltage for the diode in this circuit is exactly equal to Vp. Now, strictly speaking, this is a misleading use of the term peak inverse voltage. The peak inverse voltage for a diode really means the maximum voltage you can safely apply in reverse across a diode. While we did say that a diode does not conduct when it's reverse biased, that's true only up to a certain voltage. Once the voltage exceeds the threshold value, the so-called peak inverse voltage for the diode starts to conduct, and unless, in fact, it conducts very heavily, and produces a lot of heat as a result. And unless the diode has been specially designed to withstand such heat production, it would be disastrous for the diode. You would end up with a burnt diode in your hands. So it is important to know how much of an inverse voltage you can apply across a diode if you want to use it in a rectifier circuit. So the PIV really is a measure of the diode and not the circuit, and definitely not of the signal. However, it's common usage, though slightly faulty usage, to use the word peak inverse voltage in the sense that I have used it in right now. In a circuit, say in this case, in this half-wave rectifier circuit, the peak inverse voltage also refers to the maximum inverse voltage, maximum reverse voltage, which is dropped across the diode. There is of course a connection between the two usages of the word. You have to make sure that this voltage, in this case Vp, does not exceed the rated peak inverse voltage for your diode. So if a diode has a breakdown or voltage or peak inverse voltage rating of say 150 volts, you had better make sure that the input sinusoid that you are applying across it in this rectifier circuit has an amplitude which is smaller than 150 volts. Otherwise, your circuit will simply break down. Okay, so the peak inverse voltage is a concept that has to be kept in mind when you're designing a rectifier circuit. Now let's take a look at the output from this rectifier, and let's simplify things a bit for ourselves. Let's assume that we have an ideal diode, that is, a diode which does not conduct at all in the reverse direction, and in the forward direction conducts without any resistance. So if that is the case, of course, what will happen is, in the reverse bias situation, that is when the input voltage is negative, no current will flow in the circuit, so the output across the resistance will be exactly zero. And in the forward bias situation, when the input voltage is positive, there will be no drop across the diode, current will flow, and the entire input voltage will be dropped across the output, which is why the output in this case will be the purple curve that you can see here, just this one, which completely follows the input, then flat, then again the purple curve, and so on. So this is when we get a perfect half-wave rectification, which is easy to describe mathematically by this formula that VOT is Vp sine omega t. Well, when t is between 0 to pi by omega, so the first half of the period is 0 for the second half of the period, pi by omega to 2 pi by omega, and of course it's periodic, so it keeps on repeating after 2 pi by omega. Of course, this is a good approximation for a real diode scenario when two things hold. Firstly, the peak voltage has to be much bigger than the cut-in voltage V gamma, which was clearly being violated in the picture that we drew a while ago, but that was essentially drawn to emphasize that there is a cut-in voltage effect. But if your input voltage is much larger, then you can simply ignore V gamma. Also, you should be able to ignore the diode resistance, the forward diode resistance small rd with respect to RL. Strictly speaking, what you should really be able to ignore is not only small rd, but small rd plus the other resistance in the circuit which you cannot see in the circuit diagram, which is the source's own resistance. So typical source resistances are also rather small, and small rd, as we have seen, is 26 millivolts divided by ID into eta if you have a silicon transistor, silicon diode, and that's a few tens of ohms. So if you are using a RL which is of the order of kilo ohm or so, this is usually a very good approximation, and you get near perfect half-wave rectification in most situations like this. Of course, if you cannot use the ideal diode approximation, you can still use a diode equivalent model, which is you mimic your real diode with an ideal diode in series with a cut-in voltage battery in reverse and a small RD resistance in series with it. And if you take that into account, the output voltage works out to be RL by RL plus RD. So that's the voltage division formula, series voltage division formula, into Vp sine omega t, which is the input voltage, of course, minus V gamma. So there's a V gamma drop across the battery. You take that out and you get Vp sine omega t minus V gamma is the voltage drop in the small rd capital RL combination. Capital RL gets RL by capital RL plus RD part of that. This happens of course when sine omega t exceeds V gamma by Vp. That is when you have a forward bias input, sufficient forward bias to overcome the V gamma. And of course, otherwise is 0. Now, as I pointed out again, the formula here would be RL by RL plus RD if we could ignore the source's resistance. If we cannot ignore the source's resistance, there should be a plus RS term as well here. And in most cases, RL can be pretty big compared to RD and RS. But in general, but in particular, if we cannot make such assumptions, what we will usually get is this result. The maximum output voltage, the peak value which this will have, of course, their Vp reaches this maximum value, which is just Vp sine omega t's maximum value, which is Vp. And this is the maximum value for the output voltage. Here I have explicitly shown the effect of the source resistance. So in case you are wondering, the previous formula should also have had an RS in the denominator. We just suppressed it till then. But here we are being more exact. It's not only the diode forward resistance which causes the output to be less than the maximum possible Vp minus V gamma. Source resistance also has a say in it. After all, some part of the net voltage Vp minus V gamma will be dropped across both the source and the diode, as well as the bulk which should be across RL. So this is your formula for the output voltage, the maximum value or the peak value of the output voltage. Now, let's take a look at some special mathematical properties, especially of this ideal diode rectifier. We are still talking about the half-wave rectifier, remember. So this is the output. This purple curve here follows faithfully the input in this half of the cycle, then it's 0, then again the input, and so on. So VOT is just Vp sine omega t for odd halves of the cycle and 0 for even halves. That is, from the beginning of a cycle to mid cycle is Vp sine omega t. From mid cycle till the end of cycle is 0. So that's a mathematical expression for VOT when you have an ideal diode, which is a decent approximation for most real situations. Now in this case, the question could be, what would a voltmeter connected across the output really measure? If it were a very, very good voltmeter capable of responding very, very rapidly, it should actually show a voltage which keeps on changing with time. But most voltmeters have a response time which is a lot bigger than time in which this sinusoidal voltage would change. So if you have connected a DC voltmeter, what it would really show is the average value of the input voltage, not the instantaneous value. And how do you define the average value? Mathematically, it is defined to be the average value to the limit of this quantity, tau going to infinity limit of the integral from 0 to tau of VO t dt, that is, you integrate the voltage from 0 to tau over a large time interval, divided by the time interval. This quantity, at least in the limit as tau goes to infinity, is what is called VDC. It's very straightforward to calculate this for our particular VOT, the simple mathematical formula here. And since this is really periodic, it's easy to see that you can calculate over one period and that will give you the right answer. You don't have to really calculate for a very large period of time. And the calculation is straightforward. You should be able to do the integral yourself. And you can show easily that VDC, this average, works out to be Vp by pi. So it's less than 1/3 of the peak value of the voltage. So this voltage goes up and down quite a bit. The DC value, the voltage which a DC voltmeter would show, is rather small. It's actually Vp by pi. Similarly, IDC, the current which is in the circuit here, also has an average value. And since it has exactly the same variation with time as VO, it's easy to see the current will also be of the same form. The DC value of the current will be the peak value of the current divided by pi. So this rather small value for the DC part of the voltage or the DC part of the current essentially shows that despite being in one direction, this is really not a very good DC. It's in one direction, but it goes up and down quite a lot. In fact, we could actually write the current and also the voltage very similarly, current through the circuit in this form. This is nothing but a Fourier series decomposition of this half-wave rectified output. I urge you to calculate the Fourier series decomposition yourself for this function. It's pretty straightforward. All you have to do is a few integrals. The average value, of course, sits in the constant term in the Fourier series. That's what you have already learned about Fourier series. The average value of the function is A0. In addition, you have one sinusoidal term and a bunch of cosinusoidal terms of different frequencies. So, these are, of course, all terms which go in both directions, positive and negative. The overall voltage doesn't, because of this average value which pushes the whole thing up. So, although the overall voltage goes in only one direction, it really has a substantial amount of alternating signal in it. So, apart from the IDC, which is IP by pi, the rest of the current is actually called the IR. R here stands for ripple. This is the ripple on top of the current, and it's actually the AC part. A measure of how good this rectification is, how good a DC do I get out of a rectifier, is something called the ripple factor. What we do is take the RMS part of the ripple, which is the RMS part of the sum total of all these terms, which tells you how big the ripple is, and divide that by the DC value of the current. So this ratio is what is called the ripple factor. The smaller it is, the better is your rectifier. Now, it looks like a substantially hard task to calculate the RMS value of this entire sum here, but there's a rather simple trick which allows you to calculate it without very much of difficulty. This will be part of your assignments, and once you calculate this for the half-wave rectifier, it turns out to a pi square over 4 minus 1, assuming, of course, ideal behavior. And this number is 1.21, which means that there is 20% more AC. It's not just 20% AC, it's 20% more AC than DC in this particular rectified output. So despite nominally being DC, nominally being one direction, this is really not very good as a DC supply. In the next part of our course, we are going to learn about how to make the output better. That is, make it closer to the ideal DC, which is flat in time. This will involve modification of the circuits a bit, and inclusion of things called filters. So we are going to come to that later. For the time being, let's just take a look at the way in which I can improve on the behavior very directly. Here you can see, of course, the half-wave behavior is pretty bad because this is bringing the average value down quite a lot. You are missing out the current completely in this half of the cycle. So a full wave rectifier, something which gives you current not only for half of the cycle but all through the cycle in one given direction, would be a much better option. And the kind of full wave rectifier that many of you have studied in your plus 12 is simply this circuit. This is a circuit which uses a device called a center tapped transformer. So you use a transformer and to the primary of the transformer you connect your voltage source. The secondary is what is connected to your rectifier, and the secondary has a center tap. It's a very accurately placed tap in the middle of the secondary coil, so that as the input voltage fluctuates, there will be a corresponding AC in the output, but because of the center tap being exactly in the middle, the voltage at the point A well, with respect to the center tap will be exactly negative of the voltage of the point B with respect to center tap. So if you look at the way the voltages behave at the points A and B with time, if A's voltage goes up and down like this in a nice sinusoid, B's will be a sinusoid too, but exactly 180 degree out of phase with A's. So this is what the center tap does for us. Of course, if the center tap is not really at the center but slightly to one side, then the amplitude of these two sinusoidal oscillations will not really be the same. So now let us try to understand the action of this full wave rectifier circuit. Again, a circuit which should be pretty familiar to most of you, but let's go through this again anyway. Notice that you have two diodes here, and if the first diode is forward bias, which happens when VA is positive, notice that the first diode is essentially connected through this resistance to the center tap. So if the voltage at point A is above that of the center tap, which is the VA here in this diagram is positive, so in this part of the cycle and in this part of the cycle, the diode is going to conduct, and if we assume for the time being that the diode is ideal, it's going to conduct without any resistance, so the entire voltage is going to be dropped across the resistance here. So the current that will flow in the circuit is this blue curve here. Of course, the current and the voltage are being drawn on the same axis. They are two entirely independent scales. They're different physical quantities. So the fact that I've drawn the blue curves smaller in height than the green curve has no real absolute meaning. It just means that they are being drawn to whatever individual scales they have. However, if I were to plot the voltage drop across the resistance because of the current, you would have followed exactly the green curve here, then flat, then the green curve again. Now this is what happens when diode D1 is conducting, which is when VA is positive. And at that time, when VA is positive, VB is negative, which means diode D2 is reverse bias, so it does not conduct at all. If you look at diode D2's behavior, it does not conduct at all, so the current through it is zero in this cycle and this half of the cycle. But in this half of the cycle, if the voltage at B which goes positive with respect to the center tap, and B is again connected through the resistance to the center tap, you are going to get a current. And if we assume that the two diodes are identical, and since the resistance R is the same in both cases, the current will be the same as in the previous half cycle through the diode D1. Now what happens to the net current through the resistance? Notice the current through D2 is in this direction, so it's into this node. Current through D1 is also into this node. So both these currents being into the node, the current through resistance, which is the current flowing out of the node, has to be equal to the sum of the two. So current through D1 looks like this blue curve, current through D2 looks like this blue curve. The current through both together, which is the current through the resistance, looks exactly like this, and the voltage looks exactly like the purple curve here. So the voltage essentially exactly follows voltage at A when voltage at A is positive, and voltage at B when that is positive. So you get a positive current or positive voltage through the entire time. This is full wave rectification. And the mathematical properties of an ideal full wave rectifier are rather simple. The DC value is just twice that of the case for the half wave rectifier, simply because in the half wave rectifier, for half of the cycle there was no voltage. Here, there is voltage for both halves of the cycle, so you are going to get twice as much average value as in the DC case. So instead of Vp by pi, it's now 2 Vp by pi, substantially closer to Vp. Also the ripple is going to be substantially less, simply because the DC part has gone up. So we are going to get a ripple which, if you calculate, square root of pi square by 8 minus 1, which is around 40%. So remember, it was 120% for the half wave rectifier. This is a substantial improvement. But what about the peak inverse voltage? Because here we have two diodes and we have to worry about peak inverse voltage across both of them. In this particular picture, I am showing you the peak inverse voltage scenario as far as diode D1 is concerned. D2 is very similar. Notice that the voltage at point A, one end of the diode D1, follows this green curve of the input, which I have redrawn here as this thin line. What about the voltage at point B? Well, for this half of the cycle, voltage at point B exactly follows voltage at point A, which means the drop across diode D1 is 0. Of course, remember that we are actually ignoring the cut-in voltage and the other such non-idealities of the diode. But what happens in the other half of the cycle? In the other half of the cycle, voltage at point A goes negative, diode D1 cuts off, but voltage at point B does not become 0. Voltage at point B climbs because now you are getting current through D2. And notice that the peak value of the gap between voltage at point B and voltage at point A, voltage at point B of course is the output voltage, both being measured with respect to the center tap. The gap between voltage at point B and voltage at point A becomes maximum here, where voltage at point A reaches minus Vp and voltage at point B reaches plus Vp at the same time. So peak inverse voltage applied across the diode in this full wave rectifier circuit is twice Vp. Of course, this means that you have to be even more careful when you are designing a circuit using this full wave rectifier circuit, because in the half wave rectifier case, the peak inverse voltage applied across the diode was only Vp. Here it is twice Vp. So you have to be more careful in choosing what kind of diode you put in your circuit so that it does not burn up because of a very huge inverse voltage applied across it.
Well, apart from this one issue of this heightened peak inverse voltage, this full wave rectifier circuit is definitely an improvement over the half wave rectifier. We do need two diodes in place of one, but diodes are really rather cheap, so using two diodes is not a big problem. The problem, however, is that we need a center tap transformer for this, an accurately center tap transformer, and such transformers are really rather expensive. In fact, if you are not willing to pay through your nose, the standard center tap transformer that you can buy from the market will usually not be precisely center tapped, which will lead to, say, fluctuations in size of the two halves of the DC output, and which automatically will add to the ripple and make your performance, well, not so good. So is there a way around this? Actually there is, and that uses something called a bridge rectifier. So called because the circuit looks very much like the standard bridge configuration that we have talked about earlier. So this is what a bridge rectifier is. It uses four diodes connected in a particular manner across the four arms of a bridge, with the so-called fifth arm of the bridge, the balance arm, being where the output is to be taken. That is, that's where the resistance RL is. And the major advantage of this particular rectifier circuit is that it eliminates the need for a center tap on your transformer, thereby reducing costs a lot. It does require two extra diodes, but as I said, diodes are cheap. Now, what happens in the circuit is that the current in the load resistance RL always flows in one direction, from right to left. To understand this, let me point out that this notation here, the plus minus sign here, of course means that Vi is to be considered positive when the voltage up here is more than this voltage. This voltage is of course nominally considered to be 0. So a positive voltage up here means this is higher than this point. And when that happens, the current essentially flows this way, and now once it gets here, it cannot go through the reverse bias D4, but it can go through D1. At this point, it's blocked by D2, so it can't go into this branch, but it can, of course, go through RL. and then through D3 and down to the ground. So this is how the circuit gets completed. The current goes like this. So the current, in this case at least, is flowing through D1 and D3. D2 and D4 are reverse biased at this stage, and the current flows in RL from right to left. So of course the voltage drop across RL is also higher on the right hand side than on the left hand side. The plus and minus being as indicated. Well, what about the situation when Vi is negative? When Vi is negative, then of course 0 is higher, the current will try to flow this way, and what will happen is once it gets here, it can't go through D3. Remember, current cannot go through a diode in the direction opposite to the arrow, which the diode symbol really represents, but it can go through D2, it can't go through D1, but it has to turn and go through RL and then through D4 on back to the supply. So for both positive Vi and negative Vi, that is for both halves of the input cycle, the current flows through the resistance RL from right to left. So in both halves, the right end is positive. So once again, we have a full wave rectification. There is current in both halves of the cycle, and the current is always in one direction. And what about the peak inverse voltage? It turns out that the bridge rectifier has an advantage in this department as well over the full wave rectifier circuit that we studied a while ago. Well, the peak inverse voltage here turns out to be just equal to the peak value of the supply voltage. And let's try to understand why. Let's go back to a scenario when the upper end was positive. So the current was flowing, and now through this diode and then this way. We are assuming ideal diodes for the time being. So when the diode is forward biased, we are going to assume there is no drop across the diode. So what is the voltage here? Well, the voltage here is of course what the input voltage is, that's Vi. So in one end of D4, which is reverse biased as the stage, the voltage is Vi. What about the other end? Notice if you go this way, there is no drop across the diode. Fine. But then the entire voltage gets dropped across the resistance because there is again no drop across the diode D3, and it's 0 voltage here. So going back from this side, we can see that this end is at 0 volts. So for the diode D4, the upper end is at Vi, the lower end is at 0. So reverse voltage across D4 is Vi at any given instant. So what is the maximum value of the reverse voltage across D4? That's of course nothing but the maximum value of Vi, which is Vp. So that's how we conclude that at least for this particular diode, the peak inverse voltage which it feels is Vp, the peak value of the voltage signal. It's very easy to see that the same argument holds for D4 in the same situation. After all, if this voltage is Vi, then so is this. Remember, no drop across D1, and this end is at 0. So the voltage drop across D2 also is Vi, and the peak value or the peak inverse voltage is Vp. This of course is a scenario for positive Vi where D2 and D4 are reverse biased. For negative Vi, the argument is very similar, and you can easily argue for yourself that in this case the voltage drop across D1 and D3, which are now reverse biased, that is in this scenario, will also have the highest possible magnitude of Vp. So this is what the peak inverse voltage is. Remember, the peak inverse voltage for the full wave rectifier happened to be twice Vp. So this peak inverse voltage is half of that. So in that sense, if we are looking specially for high voltage rectification, we don't really have to spend through the nose for very high peak inverse voltage diodes if we are using the bridge rectifier. Well, this is assuming the diodes are ideal. What happens if the diodes are not ideal? Well, not much of a difference occurs, but notice that, for example, if we go through one cycle, let's say this cycle when the diode D1 and D3 are forward biased, then assuming they are non-ideal, there will be a drop across both D1 and D3, a drop of V gamma. So twice V gamma for the two diodes. So the input voltage Vi will be dropped to a small extent across the diodes, but to the most extent across RL. The peak possible value that you will get should have been Vp minus 2 V gamma. You will not get that because there are also resistances in the circuit. The two diodes will contribute 2 small Rd, twice a diode's forward resistance to the circuit. Of course, you also have the source resistance to contend with. So what RL will get is the fraction which you calculate using the series potential division formula, RL over RL plus RS plus twice RD times Vp minus 2 V gamma. This is the maximum voltage you are going to get across RL. So this is again full wave rectification, and the full wave rectifier using a bridge rectifier has some advantages over the standard full wave circuit which uses a center tap transformer. But all of these circuits, the half wave rectifier, the full wave rectifier, all of these have one basic problem. The problem is they essentially show a large amount of ripple. Half wave shows a lot of ripple. That's reduced for full wave rectification, but still not reduced enough. After all, your rectifier circuit is supposed to replace a battery, and a battery should give you a flat voltage with time, not a voltage which goes up and down with time. So can we get closer to this ideal situation? That is the question that we are going to address next. So let me now try to describe a modification to the rectifier circuits that we have studied so far that is going to give you an output which is closer than the kind of ideal output we want. Namely, an output which does not change with time. Of course, that is really an ideal situation. What we want to do is to reduce the ripple a lot compared to what we have for the rectifier circuits. And one very simple modification, which I am going to explain qualitatively in this last section of the video today, is something which is called a capacitor filter put on a rectifier. So the circuit essentially is the circuit here, which is exactly the same as the half-wave rectifier circuit that we had described before. There's just a capacitor added across the resistance. Now, truthfully speaking, we can easily understand why addition of the capacitor should make the output better in terms of what we want. The capacitor works like a low impedance for AC and a high impedance for DC, right? It has an impedance which is inversely proportional to the frequency. So, if you can think about it this way, the current which comes in here, crosses the diode, has both DC part and a rather large AC part. That's the big ripple. However, the two parallel branches here have different impedances for the two components. The resistance has the same impedance for AC or DC, but the capacitor on the other hand almost works like a DC short and like a short for AC, but also like a rather large resistance for the DC part. So you could say almost all the direct current goes to the resistance, very little goes to the capacitor, and conversely. So if you look at the voltage across the resistance, you get a much bigger direct voltage across the resistance than what would have happened without the capacitor. So in a sense, it's sort of easy to understand why the capacitor put across the resistance should reduce the ripple. But to see this in some detail, let me take the help of a graphical representation which I have set out on the right hand side here. Okay, let me just quickly explain what these graphs are going to be. The voltage input, the input voltage is plotted here, will be plotted here, or as you will see, as I keep on advancing the animation, you will see the input voltage keep on changing sinusoidally here. Here we will have the output voltage, the voltage across the resistance, in fact the resistance and the capacitance parallel combination. Of course, there's the same voltage across both. So this voltage is going to be plotted here. I'm going to also at the same time plot the input voltage and the same curve as well again in green, just so that you can make out and compare the two, make out the difference. And here, although this is labeled VD, that's really rather wrong. I am going to plot two things here. The diode voltage and the diode current. Okay. And just for comparison's sake again, the input voltage as well. So the input voltage will be shown in all three of these graphs. But here I am going to see the output voltage as well. And that will be the prominent major part of this graph. Here you will have voltage across a diode as well as a current across a diode. So let's start the animation and see. Here we have, okay, so this is the green dot here is the voltage input. The purple dot here is the output voltage. Here you have two dots. The blue dot is the voltage and the cyan dot, the lightly colored dot here, is the current. Notice at the very beginning, we are assuming that the capacitor is uncharged and we have suddenly switched on the circuit just at the point when the input voltage is trying to rise. As will turn out, the first quarter cycle that you will see here is atypical. After this is over, the circuit settles down to a standard periodic behavior. But let's try to understand what's happening from the beginning. At the very beginning, of course, the capacitor has no charge in it, so no voltage difference here. So the entire voltage essentially gets dropped here, and which means a rather large current is going to flow through the capacitor. Notice the diode right now is forward biased because Vi is positive. And if we assume an ideal diode, which is what we are going to do for this part of the course, at least for the rest of this video, then there's no voltage drop across the diode in the forward direction. So a rather large current, this is why the cyan thing is up here, flows through the diode and ultimately it lands up mostly through the capacitor. Also, of course, there will be a part flowing to the resistance as well. The diode voltage, well, the diode is forward biased, no voltage drop. And notice what happens as the voltage keeps on rising. Of course, as the input voltage keeps on rising, the capacitor voltage follows suit. And what happens with the diode voltage? As the capacitor voltage rises to keep step with the input voltage, the diode current dies down. And now the input voltage has reached its peak, so has the capacitor voltage. And at this point, the capacitor does not charge any longer. The diode current has fallen to nearly zero. There is a small current at this stage because there is a current flowing through the resistance, because the diode is still nominally forward biased. But now what happens is this, and this is where the actual action of the filter starts. Once the input voltage starts to drop from the peak, now notice what is happening. Now the diode is reverse biased, and because the diode is reverse biased, it doesn't allow any current to flow through it. So capacitor cannot discharge to the diode. The capacitor will discharge, but it will discharge through the resistance. So notice what happened. It charged up rather rapidly through the low resistance path which is provided by the diode. So it was charging exactly in step with the input voltage. Of course, that's an approximation. We're assuming that there is no resistance on the input side, no resistance from the diode, and no resistance from the source. If there were some resistance from the source and the diode, the capacitor voltage would of course lag behind a bit, as we have already seen before. However, assuming ideal diode and ideal source, the capacitor voltage charged up in step with the input voltage as long as the diode was forward biased. But now that the diode has become reverse biased, the capacitor can no longer discharge through this. So capacitor voltage does not decrease very fast. It does decrease because it can discharge through the rather large resistance provided by RL, but it cannot fall as fast as the input voltage is falling. And that means that the diode is now reverse biased because on its left side, the P side, you have a lower voltage than on its right side, the N side. The input voltage, which is on the P side, is less than the capacitor voltage, which is on the N side. And so now, if you follow the input voltage curve that's going down, and the capacitor voltage is decreasing, but slowly. Of course, you are going to expect an exponential decrease here, but since we are looking only at the beginning end of the exponential curve, it looks more or less like a straight line decay. And if you notice the current curve here, the current through the diode is now 0. There is no current because the diode is reverse biased. What about the voltage across the diode? Now what's happening is the difference between the input voltage and the capacitor voltage. The capacitor voltage is of course the voltage at this end of the diode, and the input voltage is less. So now the voltage across the diode is negative, and as the input voltage falls further and further, and notice the capacitor voltage does not fall as fast, the diode voltage decreases rather rapidly. So this continues for quite some time, and then the input voltage starts rising again, but despite the input voltage rising, is still below the capacitor voltage, and so the diode is still reverse biased. No diode current, the cyan curve is flat. Of course, with the rising input voltage, the gap between the input voltage and the capacitor voltage rises. So the reverse bias across the diode is decreasing, but is still reverse biased, no current. And now this happens. The input voltage now catches up with the capacitor voltage. And after this, the diode gets forward biased because the input voltage is now going to cross the capacitor voltage. Now what's going to happen is that once again the capacitor will charge up rapidly through the low resistance path provided by the diode. There will be a jump in the diode current. Suddenly there will be a diode current. There was no diode current so far. That's why the cyan ball has suddenly jumped up. And now, as the input voltage increases, the same situation will repeat, except that it will be a smaller version of the same situation, because you are not charging up the capacitor all the way from 0 to the peak value. You are charging up the capacitor from just this voltage to the peak value. And during this charging process, of course, the diode conducts again. There is a current which again falls to 0. And then you have 0 diode current and a reverse bias diode as the input voltage again drops below the peak. So this behavior, a sudden spike in the diode current which then decreases to 0 once the input voltage reaches a peak, this is going to keep on repeating over and over again. So if you leave out the initial quarter cycle which you see here, the behavior of the output voltage or the capacitor voltage will be essentially like this. From its peak value is going to decrease. It's going to decrease because it's discharging through the resistance, but it's going to decrease rather slowly, and it's going to decrease until the input voltage goes and catches it again, and then it's going to, for a small period, is going to suddenly charge up, and then it's going to decrease again. Now, if you think about it a bit, notice the diode here is playing a rather strange role. It's really working by staying off most of the time. What the diode is doing here is this. It blocks the capacitor from discharging through the low resistance path back to the input. So it forces the capacitor to discharge when it's discharging only through the high resistance RL. So the discharge is slow, but periodically, once in every period here, it allows the capacitor to charge up back to the top, because it's once the input voltage crosses the capacitor voltage, the diode becomes forward biased. For a very small time, it stays on, and during that time period, it pushes the capacitor voltage back to the top. So essentially, the diode works primarily by being off most of the time, but the small time during which it's on, during which it's conducting, it actually allows the input voltage to charge the capacitor back. So the input voltage charges the capacitor to the peak value, then the capacitor voltage declines. Again, a kick comes from the input voltage, the capacitor voltage goes back up, and you end up with a zigzag pattern or a sawtooth kind of pattern for the output voltage. It's really not so much of a sinusoid, or not so much of a standard AC. It's more like a sawtooth. There is ripple here. The average value now, notice, is somewhere up here. So you can approximate the average value as the average of this peak voltage and the minimum voltage which the capacitor acquires. Of course, since the average value is defined over a large time period, the anomalous different behavior in the first quarter cycle is hardly important. You will always see the output from going from a peak to this value and back to the peak and back to this value and repeating over and over again. So the average value of the DC value will be somewhere up here. So nearly Vp. So the DC value is quite big now. It's not Vp by pi, which it was the case for the half-wave rectifier. Even the full-wave rectifier was only 2 Vp by pi. Here the average value is nearly Vp, and the ripple, of course, is rather small. Now we will estimate the ripple precisely, or at least more precisely, in the next class when we will talk about some of the mathematical aspects of this particular circuit and other related circuits. But let me just point out that it's very easy to understand that this filter, the capacitor filter, will work much better as a filter, as a way of blocking the AC from getting to the output and keeping the output nearly DC or nearly flat. It will work much better if the resistance RL is large, because then the discharge will be slow. Also, of course, if the capacitance is large, because if the capacitance is large, then the voltage across the capacitor will take a long time to change, because a rather large amount of charge has to flow through the resistance or flow out of the capacitor before the capacitor voltage can change much. A little bit of thought will convince you that what dictates the amount of ripple you have is the product RC. The bigger RC is, the slower the discharge. Of course, capacitor discharge, you all know this, is essentially controlled by the RC combination. So, R times C, I mean. And if this time constant is large, then the discharge is going to be small. Also, it stands to reason that if instead of using a half-wave rectifier, we put a capacitor filter on a full-wave rectifier, I will get even less ripple, because the input voltage then will not come back after nearly one complete cycle. The input voltage will go down and then come back again, and so it will catch the capacitor voltage here, giving the capacitor voltage less time to decrease. Hence, it will not go up and down that much. So full wave rectifier, maybe the bridge rectifier with a capacitor filter, will have an even better behavior as far as the ripple is concerned. Can we do better than the capacitor filter? Of course we can. We can try using inductances in series, for example, to block the AC from going through and only let the DC go through to the resistance. We could use combinations. We could use multiple capacitors. So there are various different kinds of filter combinations possible, each with their own advantages and disadvantages. Sometimes the cost is too high. Sometimes some other behavior becomes bad. But the basic behavior of a filter circuit is what I described here. So in the next lecture, we are going to take a look at this circuit and some other interesting diode circuits in some more detail. So until then, goodbye.